Hi, I'm Robert Kollman. I'm a Senior Applications Manager at Texas Instruments. Welcome to Power Tips. Hi, welcome to Power Tip 31. In this Power Tip, we're going to take a look at a synchronous buck regulator and how you might divide the cost of the two MOSFETs in the power stage. A synchronous buck regulator has a set of MOSFETs that average the voltage into an output filter to provide a lower voltage output, and the output voltage is always less than the input voltage in the buck. The designer is faced with a choice of, well, how large or how much resistance should be in that high side FET versus the low side FET. He might be a power IC designer and has to allocate areas that are associated with the devices, or he might be a power supply designer and has assigned cost that's associated with the two devices. One way to pick the ratios is to minimize the conduction loss. That's what the rest of this analysis is going to be based on. Here we're going to neglect the impacts of the die area on the switching losses of the power FETs and just talk purely about conduction losses. So the way that you would go about minimizing the conduction losses is recognize that the duty factor is equal to the output voltage divided by the input voltage. And so during the on time, the high side FET carries the current in the inductor, and during the off time, the low side FET carries the current in the inductor. And then we'll calculate the two resistances of the two MOSFETs, recognizing that there's a total area that's available on the die, or total cost, basically, is what we'll be comparing. And then we're going to allocate a portion to the high side FET of that total cost. So it's easy to calculate the high side FET resistance. It's just equal to the resistivity of the material divided by the area. And so for the high side FET, it's just rho divided by alpha. Recognizing that we only have a given area, A, we can calculate the low side as just rho divided by A minus alpha. And then we can also relate the parallel resistance of the devices to the total area that's available for devices. And that's calculation is shown over there on the left. And then finally, knowing the resistances of the two MOSFETs and the duty factor they're going to operate at, we can calculate what the total loss between the two elements is. This chart will help you pick the optimum area for your FETs. And basically, you have to determine what your duty factor is, and that's what these colored lines represent. This is a 10% duty factor, 50% duty factor, 90% duty factor, and the percent of the total FET area that you want to allocate to the high side FET. So for instance, if you had a 12 volt input and a 5 volt output, that would give you a 50% duty factor, and you would want to allocate your FETs 50% high side and 50% low side on here. So if you have a lower ratio of output voltage to input voltage, you want to change your FET area allocation. In this case, you'll want to operate over here and only have maybe 20% of your die area associated with the high side FET and put 80% of your die area in the low side FET. And this will minimize the conduction losses when the low side FET is operating. So in this next chart, we have plotted our duty factor, or ratio of output voltage to input voltage, on the x-axis, and then we've also plotted our optimum die area. So at low duty factors, you want to allocate less of your total FET area to the high side FET, and then as you go up in duty factors, you want to make that FET more and more of the area. And it's kind of interesting, at a 10% duty factor, you still want to allocate 25% of your total FET area to the high side FET. You can see that as you go to higher and higher duty factors, more and more area goes to the high side FET. So for more power tips, take a look at the Power Management Design website and search on Power Tips, or you can click on the link to all articles at the description section of this video. Thank you for your attention.